Okay. So I'm back. And I'm going to take this on a break now. Video number 164. And let's go on break. So. Okay, actually, somebody whispered to me. Okay. So, um, so we're just gonna call it, so these variables here in Tau Depot, let's go figure out what they are. So, open up, Tau Depot for a second. and figure out what the sizes of those variables are, right? I think they're like 8-bit integers, right? Or actually tau depot functions, my bad. Okay, so, if we go look at the tau depot put, or the tau depot get, 8-bit for these locations. Okay, so here's what we're gonna do. U08, we're going to assume that the variable has the same slots for the first two things. So U08 dex tau 000 015, and then U08 dex sub 00015, and then here we're gonna say U08 dex var so let's say that this is downstate so these are locations. These are not the actual rectangles, they're the locations. And we're gonna say we're just gonna call this camera dex 0 to 255. So it's the So this variable here, log location. Sorry, location. This location that. This is an example, and the example here so we have two of these kind of values, right? So it's kind of different than the signature here. And the reason for that is because we want to locate the camera in the down state, right? Like what would we store for the camera in the down state? And then we want to edit this camera. But we want to do it based on the mouse down position. And then a scale factor. So then we want to do int32 we want to do like we want the initial mouse down position, right? So D2X and M2X, right? So let's keep those. Initial mouse down position. Current mouse down position, right? So the vector from here to here is what calculates that drag, right? And then we also want an int32 actually, it's going to have to be a float 32 because what if we're zoomed out, right? Well, we never zoom out all the way, do we? This is a scale factor, pixels per pebble. And that's going to help make the drag line up with the cursor, right? If you don't have the correct scale factor, this isn't going to quite work. So, anyways, that's a lot of stuff. Let's do the things we can do. Let's do this. Okay. So, the first thing we want to do is just create our two rectangles, I think, right? Or, I don't know. Well, let's just do this. So, I'm tired. I am tired of this. U32, X's and Y's, zeros and ones. And then what we're going to do is we're going to get... Right, we're going to get whatever is the location of this this down viewport, right? We're going to get the location of the original down state, right? So, so this right here, EX will stand for example. And these variables here are going to go here, right? So this is going to go here. This is going to go here. Oops. And the example variables, we can steal these example variables as well, put them down here, right? So we can just say example is this. Okay? And then this P5D, whatever the heck thing here, this is the downstate variable. So this downstate location is what we're using here. And for an example, since we're using VD1, let's actually use the example of what we're actually using, right? So let's use this, right? The example case will actually be the case that we're currently writing for. So we want to get this, and we want to put them in these variables, right? So we want to get saved cam state at time of mouse down. So right here, where this code here is getting the camera state at the time of the mouse down, right? So that is what this is. So this is the camera state at the time of the mouse down. Okay. So the next question is, what we should be able to do now is load mouse So now what we should be able to do is we should be able to do a putter. So let's steal this putter code for a second. And this putter, we're going to actually just load. We're going to take this exactly, and edit a bit. So this local thing here, this is the active camera right here, viewport 1. Right, so you have a getter, we have a putter, right? And so we're going to take all these variables and we're going to put it over here, right? So low save camera, and then we're going to apply drag vector to camera. Now we're going to apply a drag vector to that camera. And we have some rectangle helper functions to help us with that, right? So if we go into like a tau type, and we look at their functions, right? We should have some type of camera operators in here, I believe, right? Zoom pole. But that's not what we want. We don't want any zooming, but there should be some type of translation. Zoom push, rec inc translate. So here's the translation code. And this is a private function. Does it have a oh, rec inc translate 256. Yes, this is actually the one we want. So we want to take this, and we want to take, we want to locate this exact thing here, right? So we put the, right? So this is how we locate that camera, right? So this is the camera that we want to do stuff to, right? So we fetch out of the save state, and we load it into these variables here, right? And then after that, we put those variables into the actual camera that is responsible for rendering. And then, after we do that, we want to translate that exact camera. So we want to use these 3 variables to locate that camera variable. And then we want to translate on the X and translate on the Y, right? And so translation is int32. And so it should be calculated with the vector for this, right? So we should be able to do this. We should be able to do something like, well, first of all, let's just call this tra ix, right? And let's call this tra iy, right? Let's not make up new names. Let's just give them the same names. And apply drag vector to camera. Well, first of all, we got to calculate that drag vector, right? So, first of all, int32, the mouse down position, the initial mouse down position. So m2x minus d2x is a vector from the down position to the current position, right? So int32 d2x add to m2x, right? Equals this. Then we can just copy this for the y, right? So the end point minus the start point makes a vector that goes from the start point to the end point, right? So these are the drag vectors, and then we want to scale them down. So we want to scale them down by pixels per pebble, right? So we're going to say that, you know, int32 translate ix equals this divided by the pixels per pebble. And we're going to take these right here, and we're going to paste this here, right? So we're going to divide by this kind of scale factor here. Now, this needs to be a y, x, y, pixels per pebble. So x's, 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 y's, 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 x's, y's. Okay, does that look good? That looks about right. Okay, yeah, so that's what we need to do, and that's all we need to do to get this working, I think. Now that is kind of a mouthful for like a function, right? To do this, but that's what we need. That's what we need to get this working. So now we know we're using 256 because the camera is bound to 256 by 256 region. So that's what we're gonna need. Tau Depot, we can close that. We had that open for reference. We can close this. We had that open for reference. Gina went. I believe we had open for reference as well. This thing we had open for reference. This thing we had open for reference. And in PAINT5D, I believe that's where we're trying to figure out this dragging code, right? So PAINT5D, odd mouse down. So this is the first mouse down right over here. And then in the first mouse down, we take the viewport 1, right? We get viewport 1. And we stash it into VD1, right? And we got to do the reverse over here, right? We get VD1 and we put it into VP1, and then we translate VP1 based on our drag vector, right? So that looks good there. So here's where we're dragging, right? So we want to just steal all this stuff and just fill it out. So this is going to be kind of a tedious process here, but let's just go with it, right? So drag, and we want to take, we got our example variables that are the correct things. So it's for the PAINT5D system, right? So we can say this memory block, the PAINT5D subsection of that memory block, and then the variables that we want to work with. The down variable, the down state variable, and the current variable, right? So this is the down state camera, and then this is the current camera. So these are camera rectangles, and these are the locations of them, right? So now for this, these are just these are all locating the data, right? So locate your camera rectangles. Okay, first step is to locate the camera rectangles. Okay. Then after we've located the camera rectangles, we want to fill it out with these things here, right? So we should have this like mouse object, right? We should have this mouse object, and it should have like these values. I don't know exactly how they're spelled out. DAO dx2. Okay. I'm just making sure that was right. So the initial mouse position, so DAO D2X, D2Y, and then M2X, M2Y, and then we're going to call this pixels per pebble. Right now we're just going to make it 1-to-1, and that's going to create some problems for us, but we'll fix that later, right? So this is pixels per pebble. This is the scale factor, which we'll need to adjust. This is the initial mouse down chord. this is the current mouse. Current mouse chord, initial mouse down chord, right? Okay, let's give that a shot. I'm excited. So, if we can just get this working, then that'd be nice. So it's not going to scroll. So we got a lot of stuff in here. Define UO8. Let's define some of this stuff. Define UO8. And it's nice. Hey, we got this drag-com thing, and turns out that we already have some common code in the drag-com, so that's nice. Then we want to define I32. What else do we have? U32 as well. So define U32. And do we have anything besides that? Is it just these three types? It looks like these three types are all we need, or all we need in here, I think. Okay. So now that we have those types, we can make a note here that we have. All right, we have these, and then in here we have undefs. All right, see ya. Good night or good morning or whatever the heck it is right now. Okay. So let's see what we got here. Undef these things. Let's remove this junk over here. Keep the checksums. 1, 2. Oh yeah, no, I stopped the So remember, remember, coffee day is Monday. I stopped the last stream because can't go over 10 hours if I want to upload to YouTube. Yeah, like I stopped last stream because, you know, I gotta keep these under 10 hours each, right? So I am not going to stop coding until I get this click drag working. Like until I get click drag working, I am not stopping. And I'm getting this click drag working because we're so close to getting like all the pieces together to get like something for my artist ready. Also, what time is it? It's like 7:33. That means that that must mean that Don Ho is doing stuff, right? Or is Don Ho done and now like Heros is working on things? Actually, let's go look at that for a second. See who's up here. Twitch.com. Let's see who is on right now. Oh, so Don Ho has already done his thing. Is that what's going on here? Yeah, because I see his name's Henry, right? Yeah, I believe his name's Henry. But yeah, so he is, yeah, so Don Ho must already be done, I think. Okay, anyways, I need to start, like, remembering to kind of visit people, like, when I'm kind of streaming through all hours of the day, where it's like, oh, hey, this person started streaming, let me go visit them really quick, you know? But I forget, so I'll get better at that. Okay, so where the heck are we? We were trying to get this running, and we defined these macros for the different bit widths that we're going to use in this function, and now it's time to give this a shot. So what we're going to expect is that the click drag, if once we get rid of the bugs, we're going to expect the click drag defaults to int. That should be void. We're going to expect that the click drag will work, but it's gonna seem like out of sync. And we'll fix that with the correct scale factor. Has no down M2X. It doesn't really have a thing called that. Because it's not called that. It's called down D2X, and then M2X is mouse. This is called pixel. My bad. Okay. And okay. So let's do P for pattern, and let's try this. Come on, no? Nothing? Nothing. Nothing, huh? Okay, not what I expected. I expected to get... Oh, wait, actually, hold on. We are already zoomed all the way out. We cannot pan if we're zoomed all the way out. Ah, yes. So we have some problems here. One of them is that the vector is the opposite way, right? So if we go this way, right? So we got to invert those vectors, and that'll be fine. We're getting closer. Oh boy, we're getting closer. I'm getting excited. So for this, we just need to, we just got to invert those vectors, right? So, we could just put it here if we really wanted to, right? We could just say 0 minus, right? We could invert them for the panning effect. Okay, so now let's give that a run, right? So now the panning will go in the right direction, but it's still not going to be quite correct. But that's not a problem because I know why it's not correct. And we already have this scale factor variable ready to fix that. But we want some feedback before we do that, right? Okay, so here we go. Okay, so now the panning is going in the correct direction, right? So if I go from, so we're up in this corner, right? We've panned all the way to this corner. If we want to pan the other way, whoop, right? We're panning the correct way, but everything is not kind of lined up, right? It's like slippery as heck, right? And it gets less slippery, right? It gets less slippery the further out we are, right? Okay, so we got to figure out the correct scale factor, right? So the correct scale factor is going to be based on taking the camera size and figuring out how many times does the camera size go into 256. So really, this definitely changed our mind here. This thing needs to be a float 32. This needs to be float. So define F32. This is going to be float. Yeah, that needs to be a float. And then down here, float 32, number 4. So this variable is a float 32. And this translate x value, what we're going to do here is we're going to say, like, we're going to cast this to a float 32 before we divide, right? And pixels per pebble, PPP, pixels per pebble, right? So we're going to just do this, right? So we're going to divide, and then after we've divided, we'll cast it back to an int32, right? So we'll do our floating point division, cast it back to int32. Okay, so before we do anything more, right? Before we do anything more besides that, we want to get this running. Want to get it running. Make sure we have the same behavior as before. Make sure that nothing weird happened with the floating point kind of nonsense. And as long as that math still works out to the same results, right? So if we zoom in here, yeah, that seems about the same. Okay. So now we want to figure out what the scale factor is, right? So the way we're going to figure out the scale factor is how? Actually, hold on. You know what? We don't even need the scale factor here, right? Because we can compute that scale factor from Well, actually, no. Okay, you know what? We're going to comment this. Never mind. You know what this is going to be? This is not going to be a scale factor. This is going to be 256. And this is going to be max window size, right? This is going to be the maximum window size. And then up here, right, instead of this float 32 for this scale factor, we're not going to use this. We're going to have a scale factor, I think. I think we're still going to need the scale factor thing. But instead of this, we're going to say int 32 okay, so this is going to be the max window size / rectangle bounds. Okay, and so we're going to have a float 32 so right now, we'll set this to 1.0, and this is going to be our pixels per pebble, right? We're still going to have to figure this out. However, this right here, this overload we're using for the tau type, we're not going to do that. So if we look at this, this overload just calls this private function with the 256, right? So we're going to call the private version, and we're going to supply it this rectangle bounds, right, of 256. Okay. So let's give that a run, make sure that we still have the same behavior. And then we'll start computing that scale factor to make the pan not all slippery as heck, right? So, but we're getting there. We're getting there. We're not stuck. We know what we're doing. We're in a good place, right? So it stops at this. That's good. Okay, so to get the to get that scale factor, we need to know the pixels per pebble, right? How many pixels is one pebble? One pebble is the smallest kind of granular unit, right? So we know the bounds is 256 by 256. So it's going to be the camera span divided by the rectangle bounds, right? So camera span, the biggest camera span can be 256 over 256. If the camera span is half of that, right, we zoomed halfway in, then, wait, maybe it's the other way around. Hold on. Oh yeah, it's the rectangle bounds. Other way around. Other way around. Okay, the rectangle bounds. So 256 over like 4 is like a huge scale factor, right? So as this rectangle gets smaller, the scale factor gets larger, right? Because this is a constant 256, and when we're zoomed in, and this is a very small number, hold on. do an example. Example, 255 divided by, let's say, 4 or 2, right? So zoomed in a lot. 256, my bad. Now, does this give us a large number? Yeah, it gives a pretty large number, right? It gives us like a 128. Yeah, that's correct. So that's a correct, right? So this is a large number. Equals large number. Uh, 256 divided by, if we're all the way out, divided by okay. So, let's make a note of this. Let's make a footnote here. It's for video documentation. Let's call this 47. Okay. So what we're seeing here in these calculations, this rectangle bounds does not change. It's always 256 here. The camera span, if we're zoomed all the way in, is this, right? And we get a very large number for our scale factor, right? Which makes sense. Or does that make sense? We get a very large number for our pixels per pebble, right? Now, if we're zoomed all the way out, then it's 1, right? This is 1 pixel per pebble, because we're zoomed all the way out, and it's a 1-to-1 ratio. That also is correct. Okay, so the camera span is the thing we got to work on. And the first thing we do is we get the camera here, and then we put it here. So the camera span, we got to say, U32 width equals x1 minus x0 plus 1. U32 height equals y1 minus y0 plus 1. Assert that width equals height. And then int32 camera span. Actually, let's do a float 32. Yeah, let's do a float 32 because rectangle bounds. How do we want to do that? Now let's just cast it. Let's just cast it before we divide it. So let's just say that this is int32 camera span equals a U32 cast of width or height, right? So we're going to merge those together because that's my way of saying it's arbitrary. They're supposed to be equal, so this is my way of taking an arbitrary selection because I don't like arbitrariness, right? So we'll cast it to a U32. Actually, no, an int32. So we have the camera span and we have the rectangle bounds, right? We got the camera span, we got the rectangle bounds. And then we're just going to, before we divide these, we're just going to say float 32 cast, right? We'll just wrap everything in the correct cast here. So we'll cast it to float 32. And then we will divide it. PPP, pixels per pebble. And float 32 and I don't know where we want to put this divisor symbol. Maybe like that? I don't know. I guess that looks kind of good. Okay, so after we have pixels per pebble, we can use that as a divisor here. And that's going to scale the translation vector accordingly to make sure that nothing's slippery. Now, if we got this wrong, everything will just be even more slippery, and it'll be pretty obvious, right? Now, if we got it correct, then everything will work perfectly, and it'll be awesome, right? So let's give that a run and see if we finally got this working. So let's P for pattern, go through here, let's scroll in, and I want it to... so it's better. I think it's better. Is it better? Oh, yeah, so it's, so it's a little bit off. Right, we can see that it's a little bit off. It's close. Right, and the snappiness is correct, right? How it snaps. That's correct. That is by design, right? So the snaps you're getting, that's by design. But we see that the panning is not quite snapped perfectly. So we have to consult. We got to think about the math that we're doing and figure out how to fix that. So obviously, at some point, we have. Yeah, something about our scale factors are wrong here. So we want to take the... Oh, hold on. Pixels per pebble, do we need to divide by the length of our vectors? So, right, something's okay, hold on. Let's run this again. Does the code... we would know that if the panning code works when we're kind of like completely horizontal or vertical, that would tell us something. So, let's try this again, because we were kind of like panning at a diagonal. If we pan at a complete horizontal or a complete vertical, does it actually start to like behave properly? The answer is I don't think so. I think it's off by 1 error. So let's go look at what we're doing here. The camera span. So you have the rectangle bounds divided by the camera span, and that's roughly the correct equation, but not quite. And why is that? Well, we want to know how many pixels Oh, hold on. Why is our math wrong? What's wrong with our math here? Perhaps we don't know what we're doing. Well, that's true. We don't know what we're doing. Rectangle bounds. We have the rectangle bounds. And if we take this large number, divide it there, we get something smaller. Yep. Is it a hypotenuse thing? Is there like a hypotenuse diagonal kind of thing going on here? I'm still like wondering if that's it. No, because it would still work completely horizontally. We would have it working, and it's not working completely horizontally. Um, so, I don't know. I don't know what the case, what's going wrong here. Could it be that it needs to be snapped? No. Well, maybe. Do you think that at some points it would work if we clicked in the wrong... If we click in the right locations, is it not off, right? So if we try to click in the center of a pixel or like the top left corner of a pixel, do we find that corrects the mistake? So we should try like the top left, the center, and the bottom right, right? So we should try those locations and see if by any chance the panning code works. So if we say we grab like right here, for example, if we grab right here, nope, still kind of wonky. Okay, what if we grab like down here, right? If we grab down here, nope, still kind of wonky. If we grab in the middle, still kind of wonky. So it looks like to me that the translation is a little bit too extreme, right? It seems like it's twice, it's double. It looks like it's double what it should be. Well, I mean, we could just, I think it's double. I don't know why it's double, but I'm observing it's double, and so we might want to think about the considerations for why it would be double. If this fixes it, then we gotta figure out why that fixes it, right? So I think this might fix it, but I don't know why it's double. I have some vague notions of why that would be. No, that's actually worse. It's worse because the translation, the scale factor, we don't want to have the scale factor. We want to double the translation. Or we want to half the translation? Let's try halving the translation. There's something that needs to be doubled or halved. And there's multiple plays we could fix it, but there's probably more correct places to fix it, where like math will make more intuitive sense. So let's zoom in here. So that's still not correct. But hold on here. Put this down here for a second. So it seems pretty decent on a it seems pretty decent, but it's still not quite correct. So we got to think a little bit more deeply about how this works, because we don't actually understand the math, right? The reason why we can't get this to work is because we don't understand the math. So we got to figure out how to make this panning less slippery. Well, actually, part of the reason is what is this? What is the region we're looking at, right? The camera is 256 by 256, and on a 256 by 256, but the canvas right now that we're mapping to is like probably 512 by 512 or something, right? So if we look at this for a second, what size is this? Because that has a lot to do with okay, so let's go open that up for a second. Yeah, we have to know. Yeah, so our calculations are a little bit not correct. If we go in here, this is probably not even a power of 2. This is probably like something. This is like whatever the camera adjusted to with that inset. So, yeah, it's like 410 by whatever, right? So this viewport rectangle that we're filling here, right? So this is VP. Yeah, so that's why I was. Okay. I see what's going on. That would explain the slippage, right? Where it's not exactly 512 by 512. That's why that division by 2 kind of worked, but didn't quite work. This is why it was still slippery. So the pixels per pebble is we have to figure out how many pixels worth we've moved, how many pebbles worth we've moved, and that's going to depend on since the VP, since the canvas viewport also, comes into play here, right? The canvas viewport. So we know we need that, right? We know we need the canvas viewport. So we have well, not the canvas viewport. The canvas viewport is the whole thing. But we need VP0, right? So so we need to throw VP0 in here, yeah. So now we need 3 variables. Jeez, we have a lot of stuff here. Loc VP 0. And let's make a note that, do we actually know what VP0 is? So VP0 means, right? So it's the destination on-screen viewport. Exactly, yes. So then in here, right, we want to make sure that we're using this correctly. Let's close this. We don't need that. So in here, we're going to fill this out. So this is the downstate camera, this is the current camera, this is the screen racked. Okay, so now we're not actually using these yet, but cam state at time of mouse down, load saved camera. Get size of on-screen viewport. Okay. And we're actually going to declare this over here, right? We're going to declare this to variable over here. We're going to reuse these. So, declare variables. We're getting there. We're going to get this. We are going to get this before tonight is over. Or today is over. Whatever we want to call it right now. So we're going to use this get function. Right? But instead of getting this stuff, we're going to get this VP0, right? So we don't have anything where we're fetching this yet, right? Nope. So we're going to fetch this VP. Let's make absolutely sure. VP0. This is the new thing, right? Yes. It's the new thing. So let's grab this VP0. Get size of on-screen viewport. That's going to be loc VP0, right? So this would be, for example, VP0. P5D VP0. VD1, VP1, okay. So now that we have this, we're going to just say that, float32, VP0 VP0 span equals VP0 span equals a float 32 cast of VP0 width, VP0 height, and then we can do U32 VP0 width equals, you know, the x1 minus the x0 plus 1. And then for the height, it's the same deal, but it's the y-axis, right? And then we also want to assert that the width and height are equal in this case. Okay, and if the width and height are equal, then we can do an arbitrary choice between the width and the height to get the span variable, right? Once we have the span variable, we need to do some calculations with that. But basically, we need to know, we need more scale factors, right? We need a scale factor where the pixels get smaller when this viewport gets smaller than the span of the camera data, right? So I think let's just say like float 32 screen pixel size, and we know that with this span right now is smaller, and so the pixel size is smaller, and so that means we're going to take this right, so if this is 255, well, hold on. No, this is not what we divide by. This canvas user view, what size is this? 256. Yeah, I thought that was 256. Okay. So 256 so that would mean that the canvas user view is the size where the smallest element is exactly 1 pixel, right? So if this rect bounds, if this is 255 and this is 255, we have a 1-to-1 ratio, right? Now, if this is smaller, then we have smaller pixel sizes, right? So we want a smaller number. A bigger number over a smaller number, not going to be correct. So let's just make that an int32 again, since it seems that we like to be doing it this way. But yeah, let's write out kind of the same. It's the same kind of formula deal, right? It's the same kind of formula dealio. But it's going to be this thing divided by this thing, It's the screen pixel size, right? So if this is 255, right? And if this is 255, then it's a 1-to-1 ratio, right? Now, if this is 512, it's twice as big. 512 over 256, right, is 2, right? Because it's 512 is twice as big. Let's check our math because I don't trust anything I'm thinking right now. Yeah, that's correct. So that would make sense for the screen pixel size, float 32. And so for the translation, we're thinking that we can take this translation and we can Alright, let's keep this screen pixel size thing over here, because we're going to need it. Let's keep this kind of division over here. Alright, keep the two divisions. So, screen pixel size, SPS. So here's the screen pixel size. Here's the pixels per pebble. And so we're going to take this float 32. And did we double wrap this? Yeah, we did. Okay, so we got to put this over here. So we're going to take this, we're going to divide by the pixels per pebble, but then we're going to multiply by the screen pixel size, I believe. And I think that might do it. I think that might do it. Now the screen pixel size is this span divided by the rec bounds, right? And the rec bounds... Okay, yeah, let's give that a shot. And if this doesn't work, then I don't know. Okay. Let's go in here. Okay, let's give this a shot. Blew up on me. Oh, that's because they're very close, but they're not quite. Because the... Yeah, okay, so I know why that is. It's because the resizing algorithm didn't quite work. That's fine. That means we're not going to use this span variable. So anywhere we see this span, so VP0 width and VP0 height. I know that because we looked at it in MS Paint or whatever, or paint.net, we noticed that the viewport wasn't exactly square. It was close to square. We're just going to say that we're going to just change this. So screen pixel size Y, right? So SPX, SPY. And so this is going to be SPX, and this is going to be SPY. So SPX and SPY. We got the viewport width. We got the viewport height. Okay, so let's give that a shot. Let's just try hacking at stuff. Let's try dividing instead, right? Because I'm out of options here. So let's just try dividing and taking some guesses. And then we know we're onto something, and we have to just account for kind of like all the transformations for this. So we'll just keep on doing this until we figure out what's going on here. Bam. Bam! Got it. Got it. Got it. Let's drag this. Now we do have to know, like, the, well, that's pretty good, right? That's like, boop. Boop. Now there's some off by ones because of the, probably not because, the pixel centers, like we click that, it seems to pretty good, though. Alright, we can click through this. So we have some asserts we need to fix, but, that's pretty good. I have, so why is it divide by the screen pixel size? Well, that kind of makes sense. It's like if we were, if the viewport were very small, then, if the viewport were very small, why is this? If the viewport were very small, what? I don't know why that is. I guess it's because I know it has to do with relative sizes. I know that's the thing, but So, oh wait, okay, let's say this width is twice as big as this, right? So the screen pixel size is twice as big as what it should be, right? Okay, I think I get it. So let's say, let's say the screen pixel size is like twice as big as what it should be. Then, no, that makes sense. Oh, because we want to go, want to go the number of pixels per pebble. Because we want to go one full screen pixel size. We want to go one full screen's worth of pixels before we translate over one, right? So at vid id, time is 1 hour, 27 minutes, and 42 seconds because we want to be cool. Okay. If on-screen pixel is huge, we need a larger raw pixel delta before the camera, before the VP 1. Camera, data camera, rect, will move by 1 pixel. In other words, we need to collect 1 screen's worth of one so if we have like a big on-screen pixel, This is like a screen pixel, and so yeah, something like this is going on. It's something like this. The formula is mostly correct. It's not completely perfect, but I think it's good enough to, like, it's good enough to where it gets me results where it's like, I'm good enough with that for now, I think. I'm not going to be like... Yeah, I mean, we can deal with what we have. Oh, also, this is not right. I'm like, what am I doing here? Okay, yeah, so, yeah, it's something like this. Right, so, if this is a screen pixel, so these are all the pixels in a screen pixel. The screen pixel size is measured in fragment pixels, right? So, so we could say a way to understand this might be that number of fragments in screen pixel. We could just say that SPX num frag chords num frags in Alright, so it's the number of fragments on the x-axis, number of fragments on the y-axis for one screen pixel. And this is like a screen pixel, right? And this is an actual pixel, and it's the fragment size, right? So that's kind of what's going on. So to figure that out, we take the on-screen viewport, and we divide by the rectangle bounds. So this is our canvas user view width, for example, and this one here is canvas user view height, right? On screen viewport, right? And now this might not always be what these values represent, but we might as well give it concrete values for the current example case so that we can understand what the hell is going on, because this is like, eh. So, click vector measured in frags, right? So this is a click vector, it's measured in fragments, right? Okay. Once we have the click vector measured in frags, we have frags, and then we have pixels per pebble. Pixels per pebble might be like frags per pebble, right? Or pebbles per frag. I don't know for sure. But then definitely we have the frags divided by something, and then divided by the number of frags in a screen pixel. Okay, yeah. So we can do the number of frags, the frags in a screen pixel, right, to get the screen pixels, and then the screen pixels per pebble. So I feel like it might read a little bit easier. The conversion might actually make more sense if the pixels per pebble is over here, right? Because it's frags frags per screen pixel it's something like this. Frags divided by frags per screen pixels divided by pixels per pebble. Is the formula, right? Like, if we're thinking about this formula, this is kind of what this formula is, right? Let's make sure that we are not full of crap here and that that division actually doesn't, like, change things. But I'm pretty sure that's the formula. There are some kind of, like, things that I might want to resolve, but, yeah, I mean... good enough for me, right? And we're zoomed in here. We can snap. Right, so it's intentionally snapping like this, right? So now you can zoom in, zoom out. Right? So you can look at there, we got one. Now we got this corner tile. And I don't know what's wrong with that. We gotta go figure out that. I mean, our code is kind of hacked together a bit. So we're gonna have to analyze that a little bit better. But yeah, the formula is this, right? So, calc, so the viewport, hold on. Okay, so I think the idea is that we can have more than one off-screen data viewport, and so the idea is that the destination is always 0, because we're only going to have one destination, but we could be sampling from multiple off-screen viewports, right? Off-screen viewport, because there could be other off-screen viewports in future. with higher number, but the on-screen viewport will always so okay, right? So, calc the off-screen data rect. Calc off-screen data rect translation, right? So right here, VP1 is viewport 1. It's the off-screen slash source slash tile map data bitmap viewport, right? That's a mouthful. VP1 is off-screen viewport because there could be other off-screen viewports in future with higher numbers. But there is only one on-screen destination viewport, so we numbered the on-screen slash destination viewport VP0, right? Okay, that makes sense to me. So let's make a note of that as well. So at the time is 1:42 and 35. How about 42:42? Yeah, will be cool. Yeah, 42:42. Yeah, sure. Okay. So let's explain this one more time. There's only one destination viewport for what we see on screen. Hence, we're going to give it a 0, right? And then if we have multiple off-screen viewports, like we're sampling different data sets and we're merging them together, they could be VP1, VP2, VP3, VP4, etc. But VP0 is always the destination viewport because we're only planning on ever having one destination viewport. We're not trying to do any multi-viewport trickery, but I could definitely see a case where we have we're sampling from multiple data sets and somehow merging them together, right? For example, parallax for some reason, right? Where we have different backgrounds and the different backgrounds that are being merged together are being sampled from different data sets and they're being merged together all into VP0. That could happen. So translation IX, translation IY. So I'd say that's good. Now I don't know if this function is gonna and this is where we apply the camera pan, right? These examples here are gonna go off screen if I indent, so we're not gonna indent because there's really nothing I can do that's gonna cleanly we could get rid of the AAC 2020, right? We could just get rid of AAC 2020. We could just call it tau depot dot those are really not bad, right? Because we understand that everything is in our project namespace, right? It's not coming from anywhere else, right? So we could just call it tau depot. And we could also make a note here. In case there's any bit of confusion. When we say tau depot here, we mean this, right? Okay, cool. Yeah, so I guess that was good that we stubbed in this common dragging code, because it turns out we needed it. And there's a lot of parts in here that I didn't even think that we would need all these. And the cool thing is right, it's kind of cool how we're working. We're not actually working with any rectangles, we're just working with those variables that are stored in the texture, right? We're working directly with those variables stored within the CPU side texture, right? That's what all these tau depot tau depot gets are for. We're working directly with those variables inside that memory. And we never have to take them out. Well, we're caching them temporarily, right? Like with these local variables. But yeah, having the canonical place for these viewports being in a place where it just naturally syncs up with the GPU memory, I think will yield some really good results in the future. I think that I'm doing some things completely crazy in a way that's going to bite me, but I think I'm doing some other things in some really good ways that are going to be like very beneficial in the future. So it's like, so let's full screen this and see if the yeah, okay, cool. And then our clicking, right? So actually, let's go to a white canvas for a second. And so Y and N, so let's go find a white canvas. I know we got a white canvas in here somewhere. So go back, where is it? Okay, so here's this white canvas. And we click here. And this is the biggest tile value, isn't it? So try to... right, and then we could go like this. Okay, and then we could zoom in. We definitely need a bit better color to mess with here, because this is not doing it for me. But right, we could just color that in like that, yeah. Right, and then we got this thingy here, and then we could can we get our pan working? Yeah, so we can pan over here, and we can start to kind of do stuff over here. So the next thing is that we want a first of all, we have to figure out all the bugs. We got to figure out all the bugs in nice. Okay, we have to figure out the bug in the fact that the code I'm using right now is supposed to set or unset a tile value. That's not what it's doing, right? So we got to figure out that. We got to figure out the bug that we're having from sometimes the assert will kind of fails us like that. We got to figure that out. Yeah, we got to figure out why that is. And we either have to just allow this, because it looks like it's off by 1, or we have to figure out why that's happening and fix it. But we're getting some good stuff here. So I do want to show my artist this. Yeah, I'm gonna show my artist this, and then so let's get like a GIF recorder. We got a GIF recorder. Let's open up our GIF recorder, and then let's use this to let's rerun this. Right, it's not perfect, but we're getting there. Right, we've done a lot of stuff. We wrote a lot of just crazy code that really shouldn't have taken so long, but we just did some weird things. I don't know if it'll benefit us or not, the way we did things, but we did them that way. So let's what the hell is this? Can we not have that in our way? Okay, so let's first of all, let's try to we can only get so small here, right? Is that what's going on here? Oh, there we go. Not too bad. So let's make this nice and small. Let's okay. So we're ready to record. No, we're not ready to record yet. Let's not waste time on this. Let's actually put it in this thing. Let's do P for pattern. Let's load the pattern in. Right, let's load this pattern in. And now let's record, right? So let's hit record. And hey, we're zooming in, and then we can pan, right? We can zoom out, we can pan, and then let's stop because we crashed. So let's go save this and see what that looks like. Let's call it icanpan.gif. icanpan.gif. And then let's just go look at what that looks like and see if the crash may have been horrible and maybe the GIF looks horrible. But let's just kind of look and see what the result was in that GIF. And if it's good enough, we'll just give that to our artist for now to show them our progress. If not, we'll make another video, but I'm getting tired here. So I can pan. It was called I can pan this thing. Okay, let's take a look at this. Okay, yeah, I mean, that works. We're getting somewhere. We're getting somewhere because we can zoom in, right? So it has panning controls. It's a little bit buggy. We got to figure out why we're off by 1. But we've gotten the hard parts done. So let's just get on I can pan. So let's go take this and go send this to our artist. So let's go on Discord. So let's type in Josh chat. Let's go find our artist. And let's show them what we got, right? So let's go. I don't know what's going to open up, so let's go put this on a different screen. Let's go. Just some memes. Nothing bad. Desktop. Delete me. I can pan. Okay, open that up. A bit buggy, but right mouse to pan works. Okay, now does this actually show the... Oh, do you have to hover over it? Okay, let's also put this on Imgur for a second, right? So we're putting this out here. Let's also put this up on Imgur, right? And then I'm getting out of here. I'm just tying up my loose ends. But yeah, I'm pretty much done. So, let's upload that to Imgur as well. And okay, and then we'll take that, uploaded to Imgur in case that first one doesn't animate. Yeah, so I don't know how this is supposed to work. Okay, there, yeah, so cool. So we've put this up on both of them are animating, so that's cool. But right, we can't see the mouse. You can't see the mouse, but the mouse grabs the canvas correctly, allowing you to do the equivalent of the hand tool in... Fuck if I remember what software that is. But hopefully you get the idea, even though the mouse cannot be seen. The zoom plus pan is all done here with mouse, and pixel setting code sets correctly, but for some reason doesn't unset when you click twice on the same location. Looking into that, once all the kinks are worked out, then I will figure out a color scheme for rendering that works in your preferred dark to light method. So they're dark to light, I believe. I'm pretty sure they're dark to light. So I'm thinking of something like this. So they like to work dark to light, so I was thinking this might be good. I kind of have to work within the constraints of how the data is set up, how the engine is set up. So the current tile sets are based on on 3 layers for everything, right? So because we have that, we have to think about that when we're doing things. So it might be nice to have some type of clickable UI for this as well, because I'll tell you that I can't really remember the mouse buttons as well, and a UI that could just give us feedback as to like where the heck we are would be nice, because like what tile set are we currently on, what layer are we currently on, things like that could really help here, because blah. But yeah, so I'd say I'm done here. I did the thing. Close that. Close this. Yeah. Yeah, I'm done. So I'm out of here. I'm out of here. Yeah, I'm out of here. So this was video 164. I'm going to hope that I put the right timestamp on. Yeah, 164 Tuesday. Mouse drag. And that's mouse drag finished. So, we need to get some bugs out, but mouse drag works. So, cool. We're out of here.